quickly give you an overview of what is happening here. So we always assume that we start with a point cloud as input, so that is our 3D scan. Then we continue with extracting features for each point. So for each point, we want to have a feature that informs us about the context and also the semantics. So how we do that is we run a convolutional neural network over the point cloud. And now the fact that this is something that we can do because we have this sparse convolutional neural network. So that really scales. Sparse convolutional neural networks means that we only represent those points in the voxel grid that are actually occupied. And also by running the convolutions, we do not make the voxel space denser. Then the second component is this transformer model that simply predicts a sequence of tokens. And the idea is now that each token represents an object in the scene. And the model is trained in a way that the token of a particular object, it actually will correlate with the features of that particular object. So here, for example, the token at this place, it will have the same features as all the points at this place of the point. So that is actually what you see here. We have our points, and then in order to extract individual instance masks, we could directly correlate each token with all the points to obtain a heat map that we can then threshold to obtain the masks. So overall, it is a relatively intuitive approach, and it is much simpler than previous methods that, for example, did center voting and required a lot of hyperparameters to tune it. And when we do that, we then get 3D reconstructions like, or 3D segmentations like this. I'm also wondering, is everything clear? Do you guys want to have any questions at this point? If not,
maybe a quick one. So is the number of instances known, or how is the number of instances determined here?
Yeah, so actually the model assumes that we have an upper bound of instances, and then we also classify the class. So what is it, a chair, is it a table? And then we simply have another class that is no object. So that allows us to reduce the maximum number of objects to the number of objects in the scene.
Awesome.
So we actually have a small demo of that. So there's a website that we set up, so you can here you can just upload. This is a scan that I recorded with the iPhone, so you can quickly try out one of these methods, and then this is, for example, what it looks like. So we have our 3D reconstructions of the environment, and then we directly can look at the semantics in the scene and also the instances. I like this kind of demos a lot because you can then very quickly try out how your algorithms perform in the real world, like not just on particular data sets. So here, for example, let me show you this. I hope you can see it. So this is a room behind me. So you can you take your phone, you scan it, and then you directly get you can see how well your algorithms really perform. Yeah, so here, give it a shot if you want to try it out. So these transformer-based models are actually quite general. They allow you to perform a large variety of different tasks. Here is another component that we are looking into for 3D scene understanding, which is floor plan reconstructions from 3D point clouds. So again, we have our input is a 3D point cloud, and now the output is a vectorized floor plan. That means we represent the floor plan as a set of polygons. So each room is a polygon, so a sequence of corners. Now the underlying backbone is a little bit different from the previous model, but on a higher level, the idea is similar. The transformer predicts a sequence of tokens. Each token now represents a corner of a room, and by splitting up this long sequence of tokens, each split corresponds to a room. And then by following the order of the predicted tokens, we can obtain the individual corners of the polygons in the room. Now, I didn't visualize these, but of course, for these rooms, but these rooms are, of course, also predicted. And then you can get, yeah, so here we have now the 3D scan as input. And then we can predict the polygons of each room. And then actually what we can also do is predict the individual room types and also the doors and windows. Now, the doors and windows, they actually parameterize the same as an individual room. We simply assume that we have only 2 corners, so it's just predicted as a segment that we use for doors and windows. Yeah, this method also works reasonably well. So there was a CVPR paper from last year now. Here just an additional qualitative results. So the point that I want to make is that overall these methods, they work reasonably well for a number of tasks. For example, for segmenting objects in the scene, for getting the floor plans. And then another thing that is missing, maybe that's a quick question for you guys at the moment. If you look around yourself, what is missing beside objects and walls and doors and so on?
Well, people.
Yeah, that's exactly the thing. So we have people. So we actually can apply the same method for, that is what we did here with recordings on Kinect data. We want to extract the individual instances of people, so each person in the scene, and then also the individual body parts. That is quite interesting when we want to, for example, learn from how people interact with scenes. In principle, the model architecture is very similar to what I showed you before. Now each subset of tokens corresponds to a person, and then the individual query tokens, they correspond to body parts. So I think the more interesting aspect of this work is that in order to train such a model, it's relatively hard to capture data of real people reasons, but then second also because it's quite tedious to annotate the individual body parts. So instead, what we did here is we actually have a combination of real data and synthetic data, but what we do is we pre-train our model on a large amount of synthetic data. So we have here a real scene from ScanNet, and we generate synthetic humans into this 3D scene using a method called place. Now you see, of course, it's not extremely realistic how these people interact with the scene yet, because we can train so much data, we can then actually the models learn to pick that up, and then in the second stage we fine tune on a little amount of real data that we have. Right, and then again the quick test how well this actually works is here we see now people in. So this was actually a poster session that I recorded the people where they were presenting the work, and then we can see the body part segmentation. All right, so that gives us pretty much the overview of the individual works that we did, so we can reconstruct objects, the floor plans, as well as people. Are there any questions at this stage? All right, sounds good. So again, the point that I want to do is we have here, we have models that work reasonably well on a large variety of tasks. And now when we take these models into, when we apply them, let's say, into the wild, so I like to go around and scan individual things and then directly try out how well do they perform. So here, for example, we see a flat of a friend. I scanned it, and then we can see the predictions to make a lot of sense. However, if we now take it to let's say to a little bit more exotic, so if you go a step away from the training distribution, here we see a workshop. So it's actually a scene from the new ScanNet++ dataset. So known objects like here, a table and a chair, they are well recognized. However, when we go to a little bit more exotic objects here, like a milling machine, for example, or a saw, these are of course objects that because these are all fully supervised methods. These are objects that have never been seen during training, right? So they are then wrongly recognized either as a mattress or pillow and so on. Another example where we show, boats, this is also something that has never been seen during training, so they're falsely recognized as steroid. Now, maybe this is not too surprising because the models can only recognize those classes that they are trained on. So then the question is, how can we achieve this open vocabulary 3D scene understanding? How can we go beyond this closed set of training classes so that we can really segment everything? And so actually this is a popular approach that people are doing in the fields in the last couple of months, is that they are using visual language models, like CLIP, for example. Now I'm not sure, I guess you guys are familiar already with CLIP, so it's, I'm not sure how much in detail I have to explain it. So it pretty much consists of these two components, right? Or in general, visual language models, like we have a text encoder, we have an image encoder, and they are trained in a way that when the text pretty much describes the image, then we achieve like the features that are computed, they are similar. On the other side, if the text does not correspond to the image, then the features are dissimilar. And that allows us to do zero-shot segmentation. So for example, if we want to know if there is a cat in the image, we can simply compute the similarity between those features. If they are similar, then we have a positive response. If they are dissimilar, we have a negative response. This concept is clear, right? So, so this is pretty much the general approach that most methods are following in the field. Now there are some very recent works that came out. They have slight variations of that. But in general, what people are doing mostly these days is that they have some kind of scene representation. Like here, we train the nerve, and then next to the RGB color and the occupancy or density, we also attached the clip feature, so that we have the clip feature in this implicit nerve representation. And then now, if you want to look, if you want to search for individual objects or type of classes, you can simply take the text encoding of the objects that you're interested in, and then compute the similarity to all the features in your 3D representation. And I think currently the main challenge is, how do you actually get the 3D representation? How do you get the clip features into the 3D representation? So one approach here is, as I mentioned, is training a nerve that directly so that is supervised with 2D clip features. So the original clip actually gives you one global feature for each image. But then there are variations of that. For example, OpenSeg, that gives you, it's a model that predicts you pixel-aligned clip features. So here you then have a clip feature for each pixel. And then when we train a nerve, we can then move these features into 3D space. I think this is clear. I assume. Now, this is, of course, an implicit representation. So that can be like, for some applications, it might be too slow to actually render it all the time. And additionally, you actually have to position the camera in the right way. So pretty much you already know at what space you're looking in order to detect your objects. So here, and I think this will be now, this is one of our very recent works where we applied these mechanisms to 3D scenes for instant segmentation. Before, there have been methods, for example, like OpenScene from Sungyu, that do the same mechanism on a point base, and then they predict you a heat map. However, here, when you have multiple objects of the same type, it might not be enough to have simply a heat map distribution over multiple objects. Here, we wanted to really get to be able to extract individual instances of objects. So this is our.
I just had a quick question. If that's okay.
Yeah, sure.
Yeah. So just thinking about the last slide, the OpenSeg nerf integration. So I guess, do you have to worry about like averaging across views in the sense that, like, maybe not. So like,
No, it is a thing.
In
It
this
is a thing.
case, because it's a NeRF and it's just a generative model, it's going to guarantee that any point in 3D space is always going to generate the same OpenSeg embedding.
So once it is trained, yes. However, during training, there are some tricks that, like during optimization of the NeRF, there's some tricks that you have to make sure. For example, because you compute the OpenSeg features individually for each image. So sometimes, depending on the viewpoint, they do not they change, right? So they are not multiple.
They're inconsistent. Yeah,
exactly. So then one trick that you do, for example, is that you do not backpropagate the gradient completely to the beginning, so that you don't mess up the NeRF at that point. So these are standard tricks if you're using representation.
Okay, so you just sort of accept the fact that there's some variability over the embedding at some sort of point, and then you just sort of let the neural network just sort of figure out what it wants to predict as the embedding,
exactly,
and go from there. Okay.
So this, if you're working with implicit representations. Now, here we have an explicit representation. And so again, the goal is given a mesh reconstruct or any kind of reconstruction of a scene, and then given a search query, we want to be able to find individual object instances in a 3D scene. So here, for example, now, yeah, I guess the point that I want to make here is also that we have multiple things that we can do now. So we can, similar as before with the fully supervised methods, we can search for simply objects that are in the scene here, for example, footrest. But we can also go beyond that. We can have more general queries. We can ask more general questions, like, for example, the side table with a flower vase on it. So here you see you have actually two tables in that particular scene. One table is empty and the other table has a flower on it. And that is something that, of course, such more complex queries wouldn't be possible with the fully supervised method. So this is just to motivate a little bit, like this kind of, to highlight the power of these visual language models. You can really have fine-grained queries here. Or here, for example, you can ask for a comfy seat, or further here we can also you can have very detailed queries, like, for example, a floral print on this. You actually see the image on top on this particular armchair. And again, so this is pretty much how how it works during inference, right? So we have a 3D scene representation that we can directly query for arbitrary text queries. Now the key question is actually, how do you get to this 3D representation that you can query for? Yeah. So the approach that we follow here is we assume that we have a post-RGBD sequence, which is something that you can get easily with today's sensors, and then we obtain a 2D reconstruction from this RGBD sequence. And then what OpenMass2D does here, so the name actually comes from because it's very similar to Mass2D, but then we allow it to have open vocabulary features. What we want to obtain here is instance masks. So we have a segmentation here of the 3D scene. And then for each segment in the scene, we want to obtain a clip feature that is attached to that particular segment. Now, how does that work? Well, because we have already a model that does pretty well in segmenting the scene, we employ here Mass3D to obtain the segmentation of the scene. However, we ignore the semantic class, because now we want to operate in an open vocabulary, so we don't want to limit ourselves to only predicting masks that are actually in our set of training classes. And that is, so it's pretty much the same. It's the same architecture, except that we remove the head to predict the semantic class. Then now the question, so once we have the instances or the masks of the objects in the scene, the question is, how do we attach the clip feature to each segment? And you remember that when we want to compute the clip features, we actually need the image. So the idea is that we now look at the individual instances, for example, this pink chair over here, and we project it into all the camera views that was used to get the 3D reconstruction of the scene. And now we have a nice image representation from which we can compute clip features. Now the question, of course, is how do we select those views that are the most useful for getting a clip feature? Now, if we point the camera in a random way, compute a clip feature from there, that's of course not helpful for this particular instance. So instead, what we do here is we take the 3D points that correspond to that particular instance in 3D scene, we project it to all the frames, and then we only select those frames where the object actually appears. And additionally, we also compute, so we have this visibility score that we check how many points are actually visible of that instance so these are the vertices of the mesh, right? So we project it into all the frames, and then we compute a score, how many points are visible in each frame, and then we select the top K frames for that. So the assumption here is, of course, maybe that's a little bit heuristic. The assumption is that we get good clip features from frames where the object is visible and not occluded too much, right? And now, in order to, so given a particular frame, we could now directly compute the clip feature from the whole frame. However, we perform one additional step, that is, we compute the instance mask of that particular object using SAM, so that we get a tight bounding box around that object. And actually, the main motivation for having this additional step is going over SAM, the segment anything model, is when you look here at the image, you see the points that are back projected onto the image. They do not perfectly align with the chair. If we would directly crop the back projected points, we would, for example, here cut off the top of the head. Now, this is due to like errors in the reconstruction and also misaligned poses of the camera sometimes. So this is where, yeah, so then we follow this approach where we actually query SAM based on these on the points that we get from the 3D reconstruction that allows us then to get a nice mask that is aligned to the image. And then what we also found helpful is, instead of taking only one tight bounding box, we take multiple scales. So we give it a little bit of slack so that we can also encode context of the scene behind it. Because if we have a chair in a living room that might, or compared to a chair in an office room, that might tell us something about whether is it a chair tweed at a dining table, or is it an office chair? So that is what we do. We have this tight bounding box from SAM, then we compute, we have multiple crops. For each crop at different scales, we compute the clip embedding, and then we simply average over all the scales, over all the crops, and also over all the views where this particular object is visible. And once having done that, we then get the, we can then, so this is then the clip feature that we attach to the individual object masks. Right, so that also works quite well. Let me quickly show. So here we have now, we have a demo that you can try. Actually, the code is available, so if you want to play with this, you can also try it out. So here we have now, for example, a number of 3D scenes that we can play around with. Here we have, for example, this bathroom scene, and we can now search for example, for soap. Now we highlight always the instance with the highest similarity score. So that's why only one instance shows up. However, we can, so if you now want to be more specific, in this particular case, we see the soap here inside the shower, where we can also search, for example, for hand soap. Then you will see that the soap here next to the sink, I hope you can actually see the soap here next to the scene lights up. Maybe if you guys want to try out a query, you can tell me something. We can quickly try it out.
So maybe just a quick point of precision first. So it seems like your heat map. Okay, so you've got your heat map there at the bottom, but then you're actually like putting a mask over the heat map to just the object that's segmented with the highest score. But so okay, so we can also see the entire heat map if we want. Okay, cool.
So this is not a heat map.
So now this is the entire heat map with where the previous was just the maximum score filtered
Exactly.
out, which is the heads up.
Right.
We do see here somehow that like the sink is like a higher score than maybe some other things that you would expect to be higher score, like
Yes,
maybe the
yes.
shampoo or the other things.
It is something that you can, I mean, maybe the sink is also something that you would use in combination with a hand soap so that the query was.
Yeah.
Yeah, and I think this is actually, so it's impressive how well it works, but I think in general, I think that is still an open question here. How sometimes the queries work well, they align well with what you think it is, but sometimes it just it doesn't work well. And I think this is currently still an open question, how to recognize when something works, when it doesn't work.
Yeah, so I was intrigued by your first example, the one where you showed that the vase on top of the side table to understand exactly how that was going to end up working. And I think now I get it. It's because you like zoom out and somehow capture the context around the object. It becomes sort of part of the embedding. But so ultimately, from all of these different scales, do you store all of the embeddings from the different scales, or do you average them somehow, or
So we do average them. We average them over all scales and also the
okay.
individual viewpoints. And that is
So
then.
yeah, sorry. I guess like I haven't experimented so much with these myself, maybe like Sasha and others on the call have, but like there is sometimes there's nice regularity in this like clip embedding space where you would expect that these like nice bigger views would somehow be all kind of close and in some kind of averaging, Euclidean averaging or averaging over some other even distance metric, you'd get something that's like the middle of a nice cluster of things. But sometimes that seems to be like not so much the case. Like you might get, as you zoom out, you might get an embedding that's like somehow quite dramatically different than something that you got at another zoom. Like, have you actually looked at the statistics over the like distribution of embeddings that you get at these different zoom levels and tried to infer like whether they're making sense?
So it's not something that we actually tried out yet, but I think this is definitely the direction forward to understand when it works and when it breaks.
Okay.
All right. So let's then briefly continue. Yeah, so this is now, so here you see, so that was one of the limitations that I wanted to mention, like sometimes it works, sometimes it doesn't work, and really to figure out when it works and when it doesn't. So another thing that I don't know if you noticed before when I presented the approach here, when in order to obtain the instances, we directly used mask 3D to obtain the instance masks. And now, of course, you can say, all right, you want to do open vocabulary segmentation. So you want to have like really a method that can segment any kind of objects. However, the segmentation method, pretty much the first step in the approach, it's based on a closed set. Here, for example, you use scannet. So one could say, okay, since you trained on a closed set, your segmentation method, it can only predict masks for objects that are already known. Now, to a certain extent, this is true. We did some experiments to check how well the segmenter, so mask3D, generalizes from seen classes during training to unseen classes during test. And we actually do observe a certain kind of generalization. So it's not like it completely fails. It does actually generalize to a certain extent. However, it is still limited. So actually then so that is one of our most recent works that we tried out is how can we fix that, right? Now, the main problem now is that we have these manually labeled data sets, right? So this is, and when you ask annotators to perform such a segmentation, of course, they have a set of classes that they want to label and so on. Now, given the existence of foundation models like SAM, for example, that really give you very good segmentation, is of course the next step, right? Can we make use of these automatically generated segmentation masks to train our 3D models? And that is actually something that we looked at here. Now, of course, the problem is SAM is a method that is trained on 2D images. So we can actually have a method that performs well on RGBD frames. However, there is a significant gap between the 2D image space and the full 3D reconstruction. So when we only have like one RGBD projection from which you can directly generate a point cloud, right? That still looks very different to a full point cloud that was recorded from multiple viewpoints. So the idea that we had here is that so in the first stage, we do exactly that. We take our image, we get the 2D segmentation from SAM, and then we use that by projecting, because we know the depth map, we can project it into 2D space, and then use that as a supervision signal for a first pre-training stage. And that actually works reasonably well and allows us to obtain 3D masks for such RGBD point clouds. And now the idea that is actually simple, but it works really well, is that we can, after pre-training, we use the same model that we called our model segment 3D. So the idea is now in the second stage, in the fine-tuning stage, we actually use full 3D point clouds. We predict a bunch of masks from our pre-trained model, and then we select only those masks that actually have the highest score. So for each mask, we can also compute a confidence score, and then we select the most confident masks in the 3D space to use that as a supervision signal for training, for fine-tuning our model on full 3D point clouds. And that it works surprisingly well. And one of the key advantages of this is also that we don't need, actually, if you think about it, we don't need any kind of manual annotations. So that is, I think, a huge advantage. Yeah, so just as a comparison here, we see on the left, you see a segmentation that we obtained with Mask 3D. Also the class agnostic version, right? Otherwise, it would only recognize objects that it has seen during training. And on the right, you actually see the same scene with the automatically created labels from SAM and then fine-tuned them 3D. Here, for example, on the bottom, you can see the segmentation masks. If you compare left and right here, the segmentation masks, they are really able to segment all the small objects in the shelf, whereas for the fully supervised method I mean, both methods are fully supervised, but for the method trained with manual labels, we see really, deteriorated masks. Yeah, so I think they are really...
Quick question for you, Francis.
Mm-hmm.
Sorry. So with SAM, we've been having this issue that, you know, the masks will depend sometimes on how close you are to the object or to the scene. So if you look at a keyboard from far away, you get the keyboard, but as you get closer, you might start getting the keys, right?
Right.
And yeah, I'm wondering, like, did you run into this issue at all?
Yeah, so that is definitely an aspect. So here, what we simply trained it with taking the image, using the standard prompting where the prompt sound is regular grid, and we simply train on all the masks that we get back. So we ignore pretty much the granularity. So we train, for example, on masks that we get for the full keyboard, but we also train on masks that we get for the individual keys. So that allows us to that the model is able to see masks at various scales. But I think also that is actually one of the questions that we're thinking about is how do you decide between the different granularities, right? The level, do you want to do the segmentation at the object level? You want to do the segmentation at the part level? And I would say this really depends on the application that you want to do. Now, in this particular case, we simply directly use the predictions from SAM and over all the levels of granularity without filtering. Yeah. Okay. So I think maybe this is I think the most surprising thing for me here, and I think also the two aspects is that the masks that we get out of this, they look really well. And the second thing is actually, if you think about it, this is something that was obtained really without any manual effort to create the training data. And I think that is something that is a strong point, that we can use these pre-trained foundation models that are actually made for different domain, for the 2D image domain, and then we can use them into the 3D space and pretty much get labels for free. So I think that really shows the power of these models. Now, here's a slide where we compare now actually our previous method, the open mass 3D, so our open vocabulary scene segmentation method, where we swapped the original mass 3D segmenter with this new method that is trained on SAM. And this is just to show that we can now find that we get a much higher granularity, because we can now also detect much smaller objects. So here, for example, in the middle, you see like the query was, so we were looking for a petal handle with mass 3D as a segmentation method. We get the full kettle, and now we can actually get the individual parts of the kettle as well, because that is something in ScanNet where mass 3D is trained on, you only have the annotations for the full objects and never the individual parts, which is something that you get in SAM, which might relate a little bit to your question earlier. Similar here for the control of the copier. Yeah, so I think that also brings me pretty much to the end of my talk. So we have also here, we just put also a demo online of this work, if that is something of interest to you, where you can directly get the class agnostic segmentation or open vocabulary segmentation, if you want, of a full 3D scene. Yeah, so actually I like this example quite a bit, because typically when you train a model on ScanNet, for example, you have problems getting the frames on the wall, because they are like the geometry, it's mostly based on the geometry that is very flat to the surface. Similar here to the stand on the table. Like if you only look at the geometry, it's very hard to differentiate it from the floor. But because we have this model pre-trained on SAM that works also on in the image domain, of course, you have a difference in the color. So then we are also able to get these parts of the scene directly in 3D. Yeah, so you can check that out as well. And that pretty much, I think, just well in time allows me to conclude. So here I have a bunch of images of the individual parts of my talk. We already had a bunch of questions during the talk. I don't know if you have more questions now to end.
Yeah, thank you for the talk. I mean, I certainly have it's kind of a question or two about future or some things. So like in these cases, I might have missed a bit or two, but like these are a lot from taking some images and then being able to piece these images together. Like, is there going to be more use in the future where you think having streaming video and more examples would be more helpful? Because you talked a lot about like having to align images. You know, if you stream video, you can make a bit more assumptions about where the images go and their discontinuity.
Right. So most of the works that I showed you, actually, they assume that we have already a given 3D reconstruction of the scene. Now this 2D reconstruction, it might come from a from an RGBD screen, but we always have this global view of the scene. So whenever we do some kind of reasoning in 3D space, we have access to the full full context of the scene. Now, if you do an online method where you have an incoming stream of RGBD data, of course, that is a little bit more challenging, because you lose this access to the global context of the scene. But of course, if you want to have some kind of online applications, then this is also a direction to look into.
Mm-hmm. Well, even if you had, instead of single clip images, to disconnect it here, but someone gave you videos, at least like 5 images of a sequence of motion instead of individual images. Because I'm starting to wonder if some of the challenges here with like being able to infer things really well are model challenges, or are they just slightly a bit of versions of data challenges. Like even this day, when I use my phone to take a picture, it actually takes like 6 pictures over half a second, even while the phone's moving. It uses that to stabilize the picture and make and remove noise. But actually, if instead it kept all those pictures from slightly different points of view and use that, would that be a way to assist some of the models and do more fine-grained analysis?
Right, right. Yeah, actually, that's a good point, and I think it's probably some kind of trade-off that you have to do. So a lot of methods that we see these days, they have some kind of the 3D representation, right? And then the question is pretty much, what do you want to store in this representation of the scene? Now, if we only store the clip features, of course, you have a pretty good your model, your representation is quite memory efficient because the clip features, they are relatively small compared to having to store all the individual images. For example, for here in the case of the segments, we only store the clip features and we do not store any of the images. But of course, by doing that, we also lose a lot of information, and you might want to go back to the original images depending on the task that you want to do, right?
Okay. Good point. Yeah, thank you.
Yeah.
Yeah. So,
Okay.
maybe I can go first because I have to run. That's okay.
Okay.
So thanks for the talk. I mean, I'm not sure if you're aware, but we're working on some pretty similar lines in the group here.
I mean, I'm fully
So
aware
what
of
I've been
the concept fusion and the
Okay,
concept.
cool. Yeah. So what I've been thinking about a lot is actually like, and so maybe this is a little bit out of domain for your particular interests, but is the actual like actionability of these representations, like given that we're a robotics lab and that's what we want to do. So like I think that there's something nice about what's stored in like clip embeddings. They give you some kind of like real amazingly powerful kind of general generalist intuition about what's going on in a scene through these embeddings in this open vocabulary way. But
Yeah.
it's not so clear to me like how to project these representations down onto something that we can really truly use for planning in some specific environment, or maybe even some specific environment that we're operating in over a long period of time and observing many times, you know? I don't know. It's not really like a really well-defined question, but like, do you have thoughts about this? Like, about the actual like actionability of the representation that you get out of it, especially like conditioned on what we were talking about the unreliability of some of the embeddings and stuff like that.
Yeah, I think it's a very good point because now, or at least coming from the computer vision background, you currently it's a lot focused on the individual objects, but going forward, you also might to think about the interactivity with the scene, right? The functionalities of the individual objects. Now, if you have so actually it's something that we are looking into. So here, for example, we have what I showed you is pretty much that we have like this. You can search now the 3D spaces for particular objects, maybe even concepts. But you could also think about, I mean, if you want now to have it, so I guess you know the spot robot right here. You want to pick up a coffee cup. So the first step, of course, is to localize the object that you want to interact with. And the second step is now, okay, having seen that object, do the clip features or do these features also tell us something about how we can interact with the object? I think that is something that we are currently also looking at. I don't think we have something specific yet. Here I can show you one example where we have, so you see the light switch here at the bottom, and then the query would be turn on the light. So it's about detecting a light switch. That is one part, but then the second part, of course, is how do I interact with that element, right? Do I simply press it, or if you have another example here is when you have the drawer that it should open, it actually has to grasp the knob. Now, and this is just a demo that we did where we have pretty much hard-coded for knobs and so on. You need to grasp it and then open it. But I think it's worth investigating. Do these features also tell us something about really how to interact with
Yeah, what we can do, affordances and other things like that. Yeah,
Exactly.
they're awesome. Awesome. Thanks so much.
All right.
Okay, sorry, those demos got me curious. So are you just kind of picking the object that has the highest click response with the query and telling the spot to go like grab that? Like, how does it work?
I mean, so at this stage, it's pretty much for demo purposes to show how well the open vocabulary segmentation of the scene works. But the demo is it's quite still, there's a lot of hard-coded stuff in there.
Okay. Thanks,
Yeah,
Francis. Any other questions?
Yeah, I'm curious about the generalization capabilities. I mean, if you're considering context, do you think it would work with just pure point clouds like laser scan without RGBD? Like, is that tested or something?
Yeah, so that is actually a very good question. So for robotic applications, probably not, because if you do such a scan, even if you do a laser scan, the resolution of them is pretty low. And even if you have like a very detailed laser scan, you run into troubles of how to like handle that data, right? Because if you have a laser scan that is very detailed, that can actually represent these small parts of the scene that you can interact with, like for example, the knob that you saw in the video to open the drawer. For example, when you do a scan with the iPhone, it simply disappears, right? It's not represented. Now, if you take a laser scan, like with a professional laser scanner, these parts are indeed represented, but it's so many points that it's hard to work with. So if you then downsample it to like a few centimeters is already too much, right? Because, or like too coarse, because you like a button like that is maybe 1 or 2 centimeters. So you have to go even below. So I think it's also a question about how do you represent the scene? And maybe for these applications, a point cloud is not the right representation. So actually, the demo that I showed you here, we used the 3D representation for rough localization, and then at the end we used the camera inside the robot to do the grasp of the object. So that was a combination of 3D and 2D.
All right, thank you.
Okay. Well, thanks for the talk, Francis. That was a great talk. Really enjoyed it.
Thank you so much for having me.
Okay. All right. Goodbye, everyone.
All right, guys.
Take care.
Yeah.